in multi-slot setting. This is a joint work with my advisor Shushin Chawla and Nathaniel Cyber. So the problem is as follows. There's a website with some ad slots to present to some users. And there are some advertisers who wish to have their ads displayed in the website. And each of these advertisers have a certain value for each user, which describes the amount of money they're willing to pay so that their ad is displayed for those users. Our goal here is to allocate these slots to the advertisers in a way that would be, first of all, social welfare maximizing, which means we want the sum of the value that the advertisers get out of this advertisement to be maximized. And second, we want the allocation to be fair to the users. And then what do we mean by that? So let's say there are two users who have similar features. So in this case, we want such users to be able to see similar ads. For example, if Alice and Bob are educationally similar, we don't want it to be the case that Bob always sees the employment ads while Alice just sees retail shopping ads. And something that we assume here is that for these ad slots, there is a certain ordering over them that all the advertisers obey that, meaning that they all prefer their ad to be displayed in the first slot, then second, and then so on. Okay, so I talked about unfairness in the advertising. So where does this unfairness come from? First of all, it could be that the bids and the values that the advertisers set for the users are themselves unfair and they're biased. There has been a lot of journalistic and empirical work done that shows this happens in major advertising companies. For example, discrimination happens based on race, gender, or age. However, this is not the only cause of unfairness. The underlying allocation mechanism can also cause that. For example, what it could do is that there could be two users who have similar features, but minor differences, and then the mechanism could turn these minor differences into major differences in allocation. For example, take the highest bid wins auction. And let's say Alice and Bob are two users who are similar, but Alice has a slightly higher bid in some feature. Well, this means that Alice is going to always see for example, ad number 1, while Bob will never see it. And this will be unfair. So regarding this, there are two approaches to take. The first is to accept the underlying current auctions and figure out strategies for advertisers in the way that they bid, so we guarantee a good fairness notion. The other approach, which is what we're taking, is to design new auctions that guarantee fairness. And the fairness I'm talking about is usually considered in 2 dimensions. First, whether we're treating users as groups or individuals. And second is whether we want fairness in the sense of similarity in allocation and outcomes, or we want a certain constraint, such as MB freeness, to be satisfied, or a bridge between the two. So this whole literature, the fairness talk started from the literature of fair classification, and the work that Al refers to talk about the concept that when two users are close to each other based on some metric, then we want their classification to be also similar. After that, the work in Invento talked about composition of fair algorithms that are fair in isolation, but now we want to see what happens when we combine them together. Kim and Sean talked about preference-informed fairness and mixed these ideas with MB freeness. And finally, Zachar et al. Introduced concept of group fairness, preference-informed fairness. So our work builds on the model of Chawla et al. There has been similar work done, but in Bayesian setting. And to the best of our knowledge, we are first to make this extension to the multi-slot click-through rate setting, which I'll describe later. And in the two work of Chala et al., there are two algorithms introduced for single slot setting, proportional allocation, and inverse proportional allocation. In this talk, I'm going to talk about inverse proportional allocation, but the same kind of generalization results hold for proportional allocation. And I will describe what this actually is. So a little more about what the setting is. In this setting, we have a universe of users that arrive sequentially. There are n advertisers who each bid a value on each user. This means that for every user, we have a vector of length n of bid values. And there are k advertisement slots. So our model of extension to multi-slot setting is separable click-through rates. So here this CTR ij basically is describing the probability that a certain user U is going to click on slot J when advertisement I is presented in it. And in this model, we can define it by these two dimensions, alpha and beta. So beta basically is the probability that the slot J is clicked generally. And as I said, we assume that all advertisers assume the same probability. So there's a decreasing probability going from first slot to the k slot. And alpha is a advertiser-dependent value where each user U, it describes the probability that each user U will click on an advertisement generally by advertiser I. And our goal here is to come up with a matrix A, where Aij is the probability that slot J is allocated to advertiser I. So I talked about the fact that we want our allocation to be also social welfare maximizing. So what is the social welfare we're comparing against? Well, let's think about how we can come up with an allocation that maximizes social welfare. So what we need to do is to sort the advertisers based on their value of B times alpha for a specific user, and then just start from the first slot and keep allocating until we run out of slots. So this is going to be the value of maximum social welfare and what we'll be comparing against. Now, before I move on to the definition of fairness for multi-slot setting, let's talk about what definition they consider in the work of Chala and Jagadisan, which we will then extend. So what this concept of value stability really is saying is that if I have two users and therefore two bit vectors, which are close to each other in a multiplicative way for every element or every advertiser, then it should be that my allocation algorithm should come up with allocations for every advertiser that are close, additively close, and they're bounded by some function f with good properties. So the function f we're talking about here is, it has value 0 at 1, and as lambda increases, it goes to 1. And this parameter L here describes the speed of convergence. And we will see how we use this parameter L in our auction design to get a result like this. Okay, so now that we saw what fairness is for a single slot setting, the generalization that I talked about to multi-slot setting, it had two dimensions. It was a slot-specific CTR and an advertiser-specific CTR. So now we want to see the effect of either of these on our extensions of fairness. So let's first consider a case where our advertisers have closed bid vectors, our two users have closed bid vectors and closed advertiser-dependent CTRs, but we want to see what will happen then to the notion of fairness when we don't know anything about the slot-specific CTRs. So here we consider a very natural generalization of that value stability notion that I mentioned. So in the single slot setting, we had a vector. Now we have a matrix. So we want the same kind of result to hold in this setting. So for every element in our matrix, we want this difference to be bounded by some constant factor of the same f. However, here, rather than just assuming that the bit vectors are closed, we will assume that the multiplication of bit vector and the advertiser-dependent CTRs are closed, which is this value we have, which we call effective value. Okay, now that we saw fairness on slot-specific CTRs, well, in the definition that we had these effective values, and effective values were multiplication of bit vector and advertiser-dependent CTRs. But we would like to know, we'd like to distinguish between similarities in values or qualifications and similarities in preferences or the advertiser-dependent CTRs. But note that we can't simply throw advertiser-dependent CTRs aside. That would mean that that would affect our social welfare. We'll get a bad social welfare that way. So to motivate our definition, let's take a look at this example. Let's say there are two users, Alice and Bob, and two advertisers, 1 and 2. And the value of advertiser 1 for both Alice and Bob is 1, where the value of advertiser 2 for both Alice and Bob is 10. So this means that the advertiser, the users are identical to the advertiser. However, the users see advertisers differently. And Bob will click on both of the advertisements with probability 1, but Alice is much more likely to click on advertisement 1 than 2. So in this case, well, we have this goal of maximizing social welfare. So we should naturally display add 1 to Alice and add 2 to Bob. And Bob is fine with that because he's indifferent between the two ads. So in this case, these preferences that the users have is in line with social welfare. However, this is not always the case. Consider the same example, except now assume that Bob also prefers to see add 1 and clicks on add 2 with probability only 20%. Now, we should still, for the sake of social welfare, allocate add 1 to Alice and add 2 to Bob, but now Bob is not getting what he wants. So what this example is showing us is that in favor of social welfare, we can't have that strong notion of value stability here when considering different preferences of the users. However, what we also see is it's not the case that we have no fairness here. We still can see that when we compare preferences of the two users with each other, the mass of allocation is really pulled towards the user that has a higher preference. With this in mind, we define value stability for users with different preferences. And well, we first consider a simple case where the two users have identical bit vectors, and then a case where they have similar bit vectors, and those vectors are multiplicatively apart by a factor of lambda. But what we really want in this definition of fairness is, well, if I consider the preference vectors of the users U1, U prime, alpha, alpha prime, and then if I sort the advertisers based on the ratio of alpha to alpha prime, what I expect to see is that once summing up the allocations over any first J slots and any first I advertisers in this order, I want this sum and mass of allocation to be more for the first user than the second. So we can see that the mass of allocation is pushed towards the user with higher preferences. And in the generalization, we simply get this term of I times F here, where I is the number of advertisers we're considering. Okay, so for the rest of the talk, so far we saw some definitions of fairness and generalization. Now we are going to see the action that I talked about, inverse proportional allocation, what it is, how we can generalize it to our setting, and what guarantees we get for it in the sense of social welfare and fairness. Okay, so what is inverse proportional allocation algorithm for single slot setting? What it does is, okay, we have just one single slot to allocate, and we have n advertisers. So we first allocate 1 to every advertiser. Then we start decreasing the allocation of the advertiser with the rate proportional to the value of the bits. Now, as I mentioned, this factor L that we're seeing in fairness is appearing here. So yeah, we decrease by proportional to the value or an increasing function of the values. We do this until the sum of allocation reaches 1, which is the total amount of slots that we wanted to allocate. Now, in order to generalize this, before going to the most general case, let's consider a case where the slots are all identical to the advertiser. So our beta and alpha values are all 1. Let's see what happens to this generalization. Well, an immediate idea that comes to mind is just to simply multiply every allocation in the single slot case by k. Well, this is all good, but if none of these values exceeds 1, if it doesn't exceed 1, then everything is good. We get the same guarantees of fairness and social welfare by simply doing this. However, well, it may very well may be the case that some of these allocations are more than 1 over k. So when we multiply them, we surpass 1. So we somehow need to reallocate these excess allocations. And if we simply throw them away, we're not going to get a good social welfare guarantee. So what we do is as follows. We kind of take a similar approach to this single slot setting, but instead, so again, we allocate 1 to all of the advertisers. We decrease with the rate proportional to the values. However, now we stop when the sum of allocations reaches k, which is what we wanted because we have k slots to allocate. And let's say that A of k is a vector that we get. Again, note that here in this simple case that I'm talking about, advertisers don't differentiate between the slots. So we don't have a matrix here. We simply have a vector of length n, which specifies the amount of allocation. Now, how can we generalize from k slot setting without CTRs to 1-bit CTRs? This is the way that we're going to define our matrix. So we allocate A1 to the first column of our matrix, and for the rest, we're simply going to consider the differences of A2 column and A1, A3 and A2, and so on. So the takeaway from this algorithm really is that the beta values did not affect our allocations. However, they necessarily do need to appear when we are computing payments for our auction. Sorry, something I forgot to mention, when we are computing this matrix, rather than feeding the algorithm with values, we need to feed it with values if we had, or effective values. So the way, so we can see that advertiser-specific CTRs are in fact appearing in our allocation. So what guarantees do we get? Regarding social welfare, we get a 1 minus L over L to the L over L plus 1 to the L plus 1 approximation. So this amount, what we need to understand from this value is that it goes to 1 as L goes to infinity. Now, what that means is that as L goes to infinity, our allocation is really becoming like the allocation that was maximizing the social welfare. And that is actually expected because these decreases that we were doing was something like V to the L over summation of V to the L. And as L increases, this means that the effect of smaller V values is going away, and we're just considering the bigger V values. And so we're getting close to the social welfare maximizing allocation. Also, this value is minimized at L equals 1 and with the value of 3 over 4, which exactly matches the guarantees of the single slot setting. And regarding fairness, as I explained, we guarantee value stability and value stability for users with different preferences, as we saw in the definitions. One other thing that I want to mention, but I'm not going to go through the details of it, is that, okay, we were talking about auctions, so we would like to design truthful auctions that maximize revenue. So what we finally show is that we can also compute payments for these auctions that we described in an efficient manner. I can talk about the details after the talk, but yeah, this is what we have, and thank you for listening.